Good afternoon, everyone. Hope you're all having a fantastic day. Today we are going to be going over some application, finally, real life calculus. Applications of derivatives. This is what it's all been working up for right here. These three example questions. These guys is what Big Kahuna has all been about. So, let me get this up here. Okay, a couple of things. It says for related rates. Now this has the potential of getting a little confusing because this is going to be one of the first times that I'm asking you to take what you know and actually apply it to a real life situation. So this has the potential to get a little hairy. So I want to make sure that what you're doing when you're going through this, apart from just following along, is that you're comprehending. Okay. These take practice. There's no easy way to say that. These absolutely will take practice. So what I want you to do during this, if you feel more comfortable, if you have the time, I'd like you to watch the video through, watch each question through first, then go back and fill in the information. Okay, so watch the question through, see how I explain it, listen to how I explain it, and then go through and you can write the information down for the question. But before we get into that, let's talk about some stuff we can do here. Related rates. These are how you solve related rates. Number one, and the most important part of this, is read the problem carefully and draw a diagram if possible. Draw a diagram. Draw a picture, okay? Number two, express the given information and the required rate in terms of derivatives and state your find and when. It's going to ask you to find such and such when time is this or when height is this. So you're going to state your find and your when. So express the given information in the required and the required rate in terms of derivatives. See, related rates are about two rates that are the same. And when we say rates, obviously we're talking about derivatives, right? So when we're talking about related rates, we're talking about related derivatives. All right, so step three, write an equation that relates the various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables by substitution. What this means is that every equation needs only one variable. So if necessary, I want you to write this down here. If necessary means more than one variable. If you have more than one variable, you need to use geometry, the geometry of the situation. You need to use what's going on, and you need to eliminate one of those variables. And you'll see what I mean by that in just a second. Number four is use the chain rule to differentiate both sides of the equation with respect to t. Let me just do this. Differentiate both sides. Okay, differentiate both sides. That's all you need. Take the derivative. And then number five is substitute the given information in the resulting equation and solve for the unknown. Now there's an acronym that you can use to remember all this stuff. And I want you to write this down right beside it. It's called DREDS. D-R-E-D-S. DREDS is diagram. Right? Diagram. Then you write down your rates. You come up with an equation. Then and only then do you take a derivative. And after you have taken a derivative, you are going to substitute given values. Sorry for the handwriting, but hopefully you're used to that by this time of the year. Diagram, rates, equation, derivative, substitute. DREDS. Easy way to remember this process. Now, a little warning here. A common error is to try and substitute the given numerical information for quantities that vary with time too early. It's very common to want to do the derivative too early. This should only be done after the differentiation. So example number 1, we're just going to go smack into it. Example number 1, water is pouring into an inverted conical tank. That's a right circular cone with a height of 16 meters and a base radius of 4 meters. All right, so it gives me a couple things here at 2 cubic meters per minute. Okay, so the first thing I want to do is I'm going to do my diagram. I'm going to draw a diagram. So it says it's a right circular cone and it's inverted. So I'm going to draw an inverted circular cone as best as my capabilities can. It says a height of 16 meters and a base radius of 4 meters. So your height is 16, your radius is 4. Let me zoom in here. Read the question along with me on your paper so you can kind of see what I'm doing. And it says that it's pouring in at 2 cubic meters per minute. Water is pouring in at 2 cubic meters per minute. Before we go any farther, water is pouring in at 2 cubic meters per minute. What is that rate representing? What does this 2 cubic meters per minute represent? What is changing here? Well, what's changing is the water in the tank, right? And water is volume. So I'm going to say that the rate of volume, your derivative of volume with respect to time, is changing at 2 cubic meters per minute. The derivative of volume, the rate at which volume is changing with respect to time, is 2 cubic meters per minute. Okay? And then it wants me to find how fast is the water level rising when the water in the tank is 5 meters deep. So it wants me to find, this is my state your find and your when. This question, let me zoom out a little bit, wants me to find how fast the water level is rising. Well, that's height, isn't it? Height. It wants me to find how fast dH dt, the derivative of height, it wants me to know how fast am I changing with respect to time when the height is 5 meters deep. All right? So I'm trying to find dH dt, and I'm given volume. Well, this is kind of unfortunate because, Mr. Ballard, I don't remember what the volume formula is. Well, if only I was nice enough to give you all that stuff. Second page, formulas for geometry. Bam! Cone down at the very bottom. Volume is 1/3 pi r squared h. So volume of a cone is 1/3 pi r squared h. So right now I've done step 1 and step 2. I've drawn a diagram. I've expressed my given information. I've labeled my rates, right? So dreads, diagram, rates, then I come up with an equation. Now with the equation here, if you have more than one variable, you have to eliminate one of them. So here's what I'm going to do. I'm not expecting you to know this right off the bat. That's why I'm teaching you this, right? Don't get frustrated. But here's what I'm going to do. I'm going to use, write this down, use similar triangles. Use similar triangles to write a proportion. What I mean by that is I know that the triangle that forms right here with my point, let me get rid of some of this brightness a little bit. I know that the triangle that forms with my point on the center of the circle and the side of the cone, that triangle has a standard ratio of radius to height, right? So in other words, r over h is going to be 4 over 16. So I can solve for r multiplied by h here. R is 4h over 16, or simplified, r is h over 4. It's a ratio, right? The reason why I'm doing this is because I have two variables right here, r and h. I've got two variables, but I need to get rid of them. I need to get rid of one of them. So I'm going to express my radius in terms of h. So here's what we're going to have. Volume is going to be 1/3 pi times h over 4 squared times h. So instead of r, I'm going to have h over 4, right? So let's simplify this stuff a little bit here because we've got a lot going on here. Let's simplify this up a little bit. This is going to be h squared over 4 squared is 16, right? So if we multiply this all together, we've got h, let's do this way. This is going to be, let's combine pi and 1/3 into pi over 3 times h squared over 16 times h over 1. Just to kind of show you where I'm going to get this, right? H times h squared is h cubed, and then pi is going to be there. We've got 3 times 16 is 48 times 1. So this whole thing is going to simplify here to pi over 48 h to the 3rd power. Now I could have wrote h in the numerator with my fraction, but since I'm trying to find a derivative, let's just leave pi over 48, since that's a number. Let's just leave that outside so we don't have to worry about doing a quotient rule, because that's just a number, right? Now I'm trying to find dh dt, right? I want to find dh dt, meaning I'm going to have to take a derivative here. So let's take a derivative. That's the next step, right? It says differentiate both sides. So let's differentiate both sides. The derivative of v with respect to time, dv dt, is equal to, we've got pi over 48 is a constant, or excuse me, is a coefficient, so it's going to stay the same. The derivative of h cubed is 3h squared, but since I'm taking the derivative with respect to time, dh dt. Okay, so again, I'm taking the derivative with respect to time. That's what number 4 says. Take the derivative with respect to time. Since none of these have a t, I'm going to have dt's in the bottom. Okay, let me pull this back up just a hair. All right, so from here, I want to get dh dt on its own. So after I take the derivative, I'm going to look back to my equation. I'm going to say, what information do I have? Well, I know what dv dt is. That's 2. So I'm going to go ahead and I'm going to plug in a 2. Equals. Let's see, we're all multiplying right here, so we've got, let's do it this way. Pi over 48 times 3. They want to know when my h is 5, so I'm going to plug in a 5 squared dh dt. Right? Simplifying down here a little bit, I get 2 is equal to, let's see, 5 squared is 25 times 3 is 75 pi over 48 dH dt. You can simplify that down a little bit, but we'll leave it for right now. So I want to get dH dt by itself, so I'm going to multiply the 75 pi over 48. I'm going to multiply by the reciprocal here, right? 48 over 75 pi. To both sides. And I'm going to get dH dt is equal to 48 times 2. It's going to be 96 or 75 pi. This can simplify down quite a bit. I'm going to go ahead and grab a calculator though, just to clarify some of this stuff here. We've got, turn that on, clear it out, just to make sure. We've got 96 over 75 pi. Open up some parentheses here. Make sure that my pi goes in the denominator there like I want it to. 0.407. So what I've got then is dH dt is going to be equal to 0.407, and this is changing in meters per minute. So let's talk about what the answer means, because if you don't look at what the answer means, then the whole problem is kind of pointless. So the question was asking again, how fast is the water level rising when the water in the tank is 5 meters deep? So I'm going to write over here, the water is rising at a rate of 0.407 meters per minute when your height is 5 meters deep. Okay, so I want you to really just kind of think about this for a second. If you had a cone, right, and it's really small at the bottom and then it grows as it gets up to the top. When you first start pouring water in, your height is going to change pretty drastically, pretty quickly, right, because it's so small down there. But then the closer you get to the top and the wider the edge of that cone gets, it starts this small and then it kind of gets wider and wider and wider. It's going to take more water to change the height because the water's spread out over a greater distance. So the rate that your height is changing at on your cone is constantly changing. So what they're asking is, what's the rate at a specific time? And that time happens to be expressed in meters in the height instead of actual time. So we don't know what time that happens, but they're asking when it's 5 meters deep, how fast is it filling up, right? And that's what the question is asking here. So that's what we had to figure out. And it happens to be 0.407 meters per minute. So until you can get the concept down, I want you to focus primarily on one area, and that's just doing these steps, exactly these steps, dreads. All right? Let's go to the next page here. This one's a little bit more down to earth, a little bit more simple. I don't know why this looks so dark on my my screen here. Oh, it's because my screen is dull. Well, that makes sense. Okay, sorry about that. Usually my screen's cranked up to max. I don't know why this looks so dark. Okay, it says a spherical balloon is being inflated, and it's being inflated at a rate of 20 feet cubed per minute. 20 feet cubed per minute. How fast is the radius changing when the radius is 2 feet? So first, let's draw a picture. Pretty balloon. Balloon. Little tab here, little squiggly string. Balloon. And it says, say it's spherical, so it's a sphere. And it says that the radius is changing. We want to know how fast. So let's pull out some of the information they gave me. They said that it's being inflated with gas at 20 feet cubed per minute. Well, that's volume, isn't it? So dV dt, my rate of my volume is 20 feet cubed per minute. My thing I want to find, so I've done my diagram, I've labeled my rates, now I'm going to label my finds, wins. Find how fast is the radius changing, dr dt, when the radius is 2 feet, when r equals 2 footsies. So draw your diagram, draw your rates, label your find and your win. That's D and R. Next comes E, equation. So the equation for volume came from, on the other page, 4/3 pi r cubed. Right? Now, we always have to check. Once you get here, check. Check, 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 check. Check it, check, 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 check. Craziness. How many variables do you have right here? Only one. Pi is not a variable. Crazy people. R is the only variable. So do we have to worry about changing anything to be in terms of R? No, we're good. Let's keep going. Okay, so I just want to take a derivative then. Fantastic. Let's take a derivative. dV dt is going to be equal to, we've got 4/3 pi. Those are all numbers, so those don't change. What's the derivative of r cubed? 3r squared. But since we took the derivative of r with respect to t, dr dt. Right? So let's simplify it up a little bit here. We've got our 3. Your 3's, notice your 3's will cancel out here. So we end up with 4 pi r squared. And it says that we want to find dr dt when your radius is 2. Well, we already know what dV dt is. We can go ahead and plug that in here. This is going to be 20. And we have 4 pi and a radius of 2. dr dt. So solve for dr dt. 2 squared is 4. 4 times 4 is 16 divided by pi. Or excuse me, times pi. So we're divide all that over. Let me do this. 20 is equal to 16 pi dr dt. For those of you who are just really, I need to show the work. Well, here's your work. Divide 16 pi over, and you get dr dt is equal to 20 over 16 pi, which is 5 over 4 pi, which is approximately, turn 4 pi, and then that's going to give you 0.398. And what is that changing at? Well, that's changing in a radius, is measured in feet, obviously, and that's changing every minute. So that's feet per minute. So what does that mean? Let's talk actual, what is it applied to my life? What does it mean? This means that the radius is changing at a rate of 0.398 feet per minute when the radius is 2 feet. Again, I apologize about the horrible handwriting. That's okay, though. Okay, so again, think about this. When you first start to blow up a balloon, your radius is really little. And then all of a sudden, whoa, it starts growing really, really quick. And it starts growing, and it starts growing. But notice that the more air you get into a balloon, the slower its radius grows because you're filling up volume, right? The slower the radius is going to grow, right? So kind of think about that. So when the radius is 2 feet, pretty big balloon, the rate that it's growing at is 0.398 feet per minute. Okay? Uno mas. Let's try and get this one done within 5 minutes, although I doubt it. If a 6-foot tall man walks away from a 15-foot tall lamp at a constant rate, say for convenience 1 foot per second, a slow stroll of 0.68 miles per hour, who cares? How fast is the length of the shadow increasing? Ah, there we go. How fast is the length of the shadow increasing? So dreads, draw a diagram. We've got a light pole. Here's the light. Here's a man. It's a man. He's 6 feet tall, right? The lamppost is 15 feet tall. Lamppost casts a light. Man casts a shadow. So blah, blah, blah. You've got a triangle, right? Okay, now you've got two distances that are happening here. So you've got to think about the rates that are happening. You've got two distances. You've got the distance from the man to the lamppost, and then you've got the distance from the man to the tip of his shadow. If you've ever walked away from a lamppost at night, you know that and it's kind of fun to do because the farther away you get from the lamppost, the faster your shadow gets really big, right? So it's changing at different rates. So I drew my diagram. What rates do I have? Well, the only rate I really have is how fast he's walking away from the lamppost. So let's say dx dt. I know dx dt, that's 1 foot per second. See, they never give me anything arbitrary in this. It wants to know how fast is the length of his shadow increasing. So I've got a couple of things to find here. First, I want to find dy dt. I want to find how fast is the length of his shadow increasing. Well, the length of his shadow is y. So I want to find how fast it's increasing. Now, I don't have a specific time. I just want an overall thing. Okay? And then B says, how fast is the far tip of his shadow traveling? Now, that's what's going to get different. Okay, so for 2, imagine this. You've got how fast he is changing, right? And then how fast his shadow is changing. So for 2, I'm going to be finding two different things here. I'm going to be finding how fast he's changing, and then I'm going to add that to how fast his shadow is changing. So I've got two things going on. I've got his shadow changing. I've got his distance from the light pole changing. So to find how fast the tip of his shadow is changing, I've got to add how fast he's moving plus how fast his shadow is moving. That will give me how fast the end of his shadow is going. Okay? All right. So, number 1, find dy dt. Well, there's a couple of things about this here. I've got two triangles in this, if you can notice it. I've got two triangles. I've got a small one here, and I've got a large one here, right? So again, I'm going to use similar triangles. So for part 1, let's set it up. Let's say that it's 15 over x plus y, so it's the long side over the long side, is equal to 6 over y. Okay? 6 over y. So I just set up two similar triangles, two similar ratios, a lot like I did on example number 1, two similar ratios. So what I'm going to do here is I'm going to go ahead and cross multiply. You get 15y is 6x plus 6y. Right, cross multiply. 6 times x plus y is 6x, 6y. Solve it out a little bit here. Get your y's on the same side. We got minus 6y, minus 6y. So 9y is 6x. I'm trying to find dy dt. Dadgummit. I want dy dt. So let's take a derivative. The derivative of 9y is going to be 9 dy dt. Could have done this at any time I wanted to. Just chose to do it now. And then 6, but notice this is not just 6 because it's x with respect to time. This is dx dt. I'm taking the derivative of x with respect to t. Ah, interesting. If you notice, they gave me dx dt was 1, right? So dy dt is going to be 6 over 9, divide your 9 over, times 1. Well, that's just 6 over 9, isn't it? Or 2 over 3. So dy dt is 2 over 3, and that's changing in feet per seconds. So the shadow length is increasing at a rate of 2/3 feet per second. Interesting, isn't it? dy dt is changing at 2/3 a foot per second. Well, this actually makes part 2 pretty simple then. Because part 2, if you'll remember, was find dx dt. dx dt plus dy dt. Well, dx dt plus dy dt, how fast the tip of his shadow is changing. Well, that's simple enough. dx dt was up here. It's 1. dy dt was 2/3. So that's 1 and 2/3, right? 5/3, however you want to write it. 1 and 2/3 feet per second. So the shadow, this is why we're saying that the shadow is getting longer faster than you're walking away from it. Right? It's getting longer faster than what you're walking away from it. So the farther you get from a lamppost, the faster your shadow is running away from you. So what this means then is that the tip of the shadow moves at a rate, or grows at a rate, of 1 and 2/3 feet per second. Correct that foolishness. Sorry. Okay. 34 minutes. That's okay. I kind of knew this one was going to go a little bit long. But make sure that you keep this handy. We're going to do a ton of practice with these. I can tell you that right now. Have a good day.